Hello everyone, this is the solution to Lab Exam 2 or Quiz 2. Now we were asked to design the function getAllPID, which uses basically a TF object GS and a given desired pool and then calculate basically all the possible PID controllers that assign two poles to or a pole pair to the given pole, and basically returns the necessary data that we requested here. So yeah, actually let's dive into it because it's pretty straightforward if we look at the template that is given to us here. Now, first of all, this is a very basic task that we have done so far many times. At this point, we know actually the structure that we need to follow. For example, we need to define a symbolic S. But there will be a few points where we need to tweak this a little bit because we are designing a function that does it for all the possible GS provided, no matter what the degree of the system is. That's going to be a little bit tricky, but not that much. So, first of all, what we need to do is we need to convert the transfer function that is given to us into a symbolic representation. Then we will define the PID controller, then we have the connection, and then we look for the zero polynomial and the characteristic polynomial. Let's do the first thing that we need to do here. We need to acquire the numerator vector, which we can do by using the numerator function here. If this is a TF object, then there will be a property called numerator. Now, since it's possible to have multiple input, multiple output systems using a TF representation, it has its special structure, but we don't really need that because we assume that the transfer function itself is single input, single output. So we don't really care about that part. We get rid of the extra dimension here. So denominator. Now, since we're at it, we could use the length of the denominator. We could also use the numerator, by the way, but I like it as a convention to use the length of the denominator because that will be most definitely the longest vector because it should be the highest order polynomial if we want to have a proper transfer function. But TF object returns a zero padded vector, so it's not that big of a deal. Well, now we know what the degree of the system is. Now we need to basically generate the symbolic version of it, where we use all the powers of S, starting from n to 0, and then all the coefficients, multiply them and add them together. Now, you could go the for loop route, where you take all the coefficients from the vector and then multiply with the appropriate S power and then sum them together. But I'd like to show you something interesting that I like to use most of the time. So yeah, instead of using a for loop, I can use some vectorized functions of MATLAB. And whenever it's possible, you should also try to do that because it's more efficient that way. Now, the thing that I need here is to generate a vector that starts with the nth power of S, and then it will decrease up to 0 because S to the power of 0 is going to be the constant term. Now, I can define this as a vector, and I can then ask MATLAB to just raise it to the power element-wise using S. So what this will end up in doing is going to be generating n, let's say it's 3, so 3 minus 1, 0, will generate me 3, 2, 1, 0 as a vector. And if I take the power, element by element power operator, it would be S cube, and then let's have this. It would be S cube, S square, S to the power of 1, and S to the power of 0, which is going to be 1. So this is going to be the vector that will result from this operation here. So let's actually test that. Yeah, that should be it. Now I have this test script here. So I have this test script here, and I have this getAllPID.m file. Now, what seems to be the issue here? Oh, this should be 0. So if we test it out, you can see I'm just generating a vector that has all the necessary powers here, s cubed, s squared, s, and 1. And since I have another vector, let's call it num. If I want to generate the numerator polynomial, then I have num, which should have basically the same size and vector. What I can do is I can use the scalar multiplication by taking the transpose of this and then multiplying it with this, because this is a 1 by n vector, or n plus 1 vector, and this is a n plus 1 by 1 vector. So it will generate me the scalar, but that scalar is going to have a special meaning, namely 1 in this case because it's the numerator, the polynomial itself. So I can repeat this operation with the denominator, and it would be ds. So let's see what that looks like. And as you can see, I've generated s cubed plus 2s squared plus 3s plus 4. The reason for that is that I had s cubed, s squared, s, and the constant term, and then I had a column vector that goes like 1, 2, 3, 4, and therefore the multiplication and sum of all of the operation gives me basically the polynomial that is desired here. And it's a neat way of creating the symbolic expression here. And we will see that this will become handy one more time during this session here. So this is basically going to be my plant. Now what I need is KD, KP, KI. So my controller, that is going to be KD times S squared plus KP times S plus KI divided by S. Due to the unit feedback structure, we will have the closed loop, which looks like Fs times Gs divided by 1 plus Fs times Gs. Now we use PZS, PCS, and num then to extract the zero polynomial and the characteristic polynomial. Now up to this point it's quite easy to code this because, well, it's obvious that we are going to look for this. But now what we need to do is we need to come up with PES and PDS, because their multiplication will be equal to PCS in terms of coefficients, and then we're going to solve that. Now, generating the residual polynomial is going to be a little bit tricky because we have an nth order system, and well, since we're designing a PID controller, it should be a n plus 1th closed loop transfer function. But then again, we have two poles, a pair of poles that are the desired poles. So as a result, we can see that the residual polynomial should have order n minus 1. So that's quite important to note here. Now the challenge here is that n can be anything, and this function should work for any n. Therefore, we need to come up with a clever way of constructing a residual polynomial. Once we've done that, we can then multiply and then solve for the solution. So that's going to be not an issue at all. Now, how can we generate this? Well, actually, we started something here. Maybe we want to continue with that. So first of all, I can generate the powers, as you can see here. That's not that problematic. So we have this one here, and it should start with n minus 1, obviously. But we need these symbolic coefficients that are quite tricky to generate. Well, there we can use the sim function here, which can generate us a vector. We give it a string e, so it will use e. And then if we provide it 1 by n minus 1, what it will do is it will generate us the following output. Here we can see we have e1, e2, and it goes on like that. So no matter what n is, by the way, let's see what n minus 1 is. You can see it's 2, so it's going to be a second order polynomial. Therefore, we can generate e1 and e2. You can see that we would rather have e2s squared plus e1s plus e0 as a mathematical convention, and we'll get to that. So since I can generate a 1 by 2 vector and the indices are going to be generated automatically, what I can do is I can just create my own E0 here. So sims E0, that's not that big of a deal. Now I have E1, E2, and E0. But I can see that the ordering is reversed here. I don't really want to have this as increasing powers, but I'd rather have decreasing powers here, or indices in this case. So I'd like to flip this around. Now I'll have E and I have E0. So if I run this, now I can basically create something like E2 S squared plus E1S plus then E0. Now therefore, I'm actually going to cut off this 0 part here, because multiplying E2 and E1 with the according powers is only necessary, but E0 can be added afterwards, so I don't really have to have this part here. So raise this to the S power here, and you'll see we have S squared and S, and then E2 and E1. I need the scalar multiplication of this, or the scalar product of this, to generate E2 S squared plus E1 S. And therefore what I need to do is I somehow need to generate a column vector here. And I'd like to generate the column vector like this, hopefully. Let's see. So it doesn't have to be a row vector, it can be a column vector if you take the transpose of this, because this is basically a vector and we take the transpose of that. It's again another vector. If it's a row vector, it is converted into a column vector. Now, the reason why I did this is because I'm going to take this approach here. So if I'm defining PES, I just want to have these powers times basically E here. But the problem with this is if I use the same way of defining it, if I use the same formula, then I need to take the transpose of E. Now, even though I know that E is going to be a real value, the E transpose, if we have E, will going to be have some conjugates in it. So let me show you that. So you can see we have some conjugates in it. So that's not something that I want to have. So therefore I cannot use the transpose of E. I also should be careful about this part here, because if I take the transpose outside, you'll see we will have some conjugates of S. So that's also problematic. That's also something that I don't want. By the way, S can have conjugates because S is going to be complex, but E is going to be real. I know that for a fact because it's a coefficient vector of a polynomial, therefore it should be real. But I'm not going to enforce it here, and therefore if I do it like this, it will take the transpose in the powers, so it will be a column vector, and then the element-wise operator will just use S, and I'm not going to take the transpose of S. So I have a column vector and a row vector E. So instead of doing it like this, I'm doing it like the following. So since this is already transposed, I'm going to use this here, but then E times is going to be the way we will basically accomplish this, hopefully. So let's get rid of this, and see what PES looks like. Now, there we go. We have E2 S squared plus E1 S. The only thing that is missing that we can add is E0. And that's not that big of a deal. There we go. Now we have a generic way of generating the residue polynomial for any type of problem that will be created in this function, because GS can be nth order, and we will automatically generate the n-1th order polynomial that is necessary to solve this problem. So that's quite nice. Once we have that, we need PDS, which is straightforward, S minus pole, and times S minus the conjugate. Now I want to have the conjugate, which is going to be like this. Now the problem itself is going to be coefs, PCS, all the coefficients is going to be equal to the coefficients of the multiplication PDS PS. And if you really want to debug it, or for some reason we might want to debug that, so let's just print out the whole problem that is generated here. There we go. Now you can see we have all the necessary stuff. We can equate them to each other. And the only thing that is left to us is to solve this problem. Now here we have another issue because, let me just comment this out. Because now we want to tell MATLAB that KDKP should be solved. And then we need all the vector coefficients here, all the coefficients of the residual polynomial, which is available to us, which is e by itself, and an additional e0. Now, if we leave out ki, it will be solving in terms of ki, so that's going to be it. Now, if we solve it, we have that. You can see everything is in terms of ki. E2 and E1 is basically solved directly. And we have KD and KP, and that's all that we need here. So, we're almost there. The only thing that is left here is now to create basically the necessary parametric stuff. For example, we have PES. Now we want to have PES in terms of the solution. So, since we've solved for the parameters, we want to plug them into the solution. And now we have another issue here, because conventionally what we do is we provide KD and then we say sol.kd and we plug that in. And we repeat this for all the parameters that is available in PES, so that we get rid of everything that is not KI. But we don't really have to do it by individual elements. What we can do is we can directly pass the struct that is generated by the sol function to the subs function, and subs will generate or get rid of the parameters that are available in the solution by itself. So all that we have to do is we just have to use subs and provide the solution and the old version. So it will generate us the new version that should be in terms of ki. So let's see if that really works. There we go. Instead of having e2s squared plus e1s plus e0, we knew that e2 and e1 were equal to 1. It substituted that, and it also substituted the ki values. So we end up in this result, which is basically almost the answer here. So we can repeat this for the zero polynomial. There we go. And we can also repeat this for KD and KP. So KD, KP, so the struct is already there. There we go. Just plug in the values that are necessary and run the tests. Now you can see that for any given plant and pole combination, we can basically generate a PID problem and solve that problem in terms of KI. The only thing that is necessary at this point would be to use some MATLAB function transform for KD and KP probably, to basically have a direct function that, if you plug in KI, will give you basically the corresponding controller parameters. You can also convert PES and PZS into some root locus plots. We didn't actually analyze the stability of the whole thing because that's not necessary in the quiz, but you can see again KI being positive is necessary and sufficient for stability for all the parameterized PID controllers. So if you have a positive KI, it will definitely be a stable one. And yeah, that's basically it. You can now go ahead and toy around with this and generate all the PID controllers that are necessary. And hope that this helped you out. I hope that it was a fun quiz.